I do always like to start with this slide to remind us of where we came from with HIV. We're coming out of nowhere in the early 80s, and by 95, HIV was the leading cause of death in young adults in the United States and heading that way in Canada. And with the introduction of heart therapy, this is the impact it's had in British Columbia in terms of all-cause mortality of our HIV-infected population. So there's the impressive declines with the introduction of HAART in 1996. But what I think I'm most impressed by is that how much this has continued, and how, as we've expanded access to treatment aggressively in British Columbia, all-cause mortality is continuing to decline. And this is despite the fact that there's more and more HIV-infected people all the time, and everybody's getting older. You probably get the impression from this that our HIV-infected population is becoming immortal. It's really, really impressive data. We're hardly seeing any deaths of our HIV-infected population in the entire province. So a lot of this in the early days had to do with drug resistance and drug activity. And I'm going to make the argument that that's less important these days, which I think is sort of easy to say. But as a bit of background, the way that we measure our drug resistance for HIV is a little different than the way we measure it for most other things. What we do is actually pull out the virus from the viral load test, make millions of copies of that, so amplify that, and then do DNA sequencing on that material. So we call that genotyping. And this genotyping really depends on us being able to look for mutations in the virus that we know are associated with a phenotypic effect or a clinical outcome effect in the patients. So for example, if we see methionine at position 184 in one gene of HIV changing to a valine, we know that this is associated with resistance to 3TC or FTC, for example. So this is one of the common most common mutations, and there's hundreds of other mutations. And I think the important thing to remember is that you don't have to remember these hundreds of other mutations and what they do and what the effect of every one is and how they interact with each other, because there are algorithms that do that. As long as we have sufficient information from patients to know what, or from studies to know what mutation has what effect, we can easily just do the sequence analysis and get results back. Where it's becoming a bit more challenging in the HIV world and in HCV world is there actually are hardly any failures these days. Almost everybody's succeeding, so it's becoming harder to know what mutation causes what level of resistance. So we're going to have to do additional studies to work that out. So, but I'll get back into that a little later in the talk. But just to give you a picture of what's happened in British Columbia over the years as we introduced therapy, in the early days, say around 2000, of the treated population that we had, about 30% of our population was untreated that we did our test on. So they were all wild type. But of the treated population that we had, roughly about a third of them had resistance to one drug class, roughly a third of them had resistance to two drug classes, and about 10 or 20% of them had resistance to three drug classes. We only had three drug classes. In essence, in around 2000 or so, accurate treatment of HIV was drug resistance, and this has completely changed these days. The vast majority of patients that we test are completely wild type, susceptible to all the drugs, and we got 6 drug classes in a pinch. In 2012, we only had 24 people who had 3 drug class resistance in our entire province, and in fact, in November last month, I signed off from British Columbia 1 test from the entire province where there was 3 drug class resistance, and that guy also had the integrase inhibitor class still to go. So in that sense, it raises the question of, maybe we should just pack it in and retire. It's all good. But actually, probably not. There's a couple of reasons I'm not going to just retire. And that's what I'm going to talk about the rest of this time. One of them is transmitted drug resistance. One of them is what we do with folks with very low viral loads. One is an argument I'd like to make that we should be looking at drug levels in the same samples we use for drug resistance testing. I'll give you a picture of what we can do with the sequence data that we collect, which is sort of more advanced analyses than we've been traditionally doing up until now. And then I'll give you an update on the integrase inhibitors and some new technology. If there's time, I'll go into what we're doing in the HCV world. In terms of transmitted drug resistance, most places around the world have been saying there's sort of 5 to 15% drug resistance overall. And that tends to be true, but what is happening is that there's an increase in clinically important drug resistance going on in the background that maybe isn't getting noticed. There's 10% NNRTI resistance in some places, 7% in other places. And that's pretty much true. Although there's no transmitted integrase inhibitor resistance to speak of, we've noticed that in parts of Canada, in say Regina, for example, or in parts of northern Ontario, up to 50% of the newly infected population has transmitted NNRTI resistance before they start therapy. So this is a concern. We can blow up all of our drugs fairly quickly if we're not careful. And this is the first signs that this is actually starting to happen. I should mention that these are two independent cases. The transmitted NNRTI resistance in Saskatchewan is a K103N mutation. It's a different mutation it's a 190 in Saskatchewan. It's a different mutation than the 103 that's being seen in northern Ontario. So you can get these pockets of transmitted resistance that can expand and expand and expand, and in the end we'll lose the drug. So let's not do that. Otherwise we're going to reverse that whole picture and go backwards. Having said that, another application besides in looking in untreated people for transmitted resistance, one of the main applications that we're using our drug resistance testing in is in the setting of pretty low level viremia, below 1,000 copies per mil. And in the US, the kits that are licensed are only approved above 1,000 copies per mil, or the only one that's remaining as a kit in the US actually requires you have at least 2,000 copies per mil of virus to get a resistance test done. And that's largely because that's where the bank of evidence to say that resistance testing was a useful thing sort of ended. So there was the guidelines question whether it would be possible to do low-level viral load testing and whether the test result was meaningful. In Canada, we've been cheerfully doing this below 2,000 copies for years, and in fact, it would be horrifying if we waited to 1,000 or 2,000 copies to do this. But we didn't really have the data at hand to show that it was really a clinically useful thing to do. So we've published a lot of this in the last year, and that's what I'm showing here. First of all, the impact of whether we can successfully give a test result at all versus a complete failure to amplify, a failure to be able to give any answer at all. And as long as the viral load's above about 250 copies per mil, we've got about a 90% success rate. So I would say we can cheerfully give you a result as long as the viral load's above 250. If it's between 50 and 250, we will give it a try if you ask if it's important. But our success rate does sort of drop off quite precipitously around that area. So I don't know if Ontario's still got a limit. Some provinces have a limit on when they'll actually forward a sample to us for testing or not. But I think the data suggests that as long as there's 250 or more, it makes a lot of sense to send it to us. So that's the data in terms of just giving you a result as a yes, yes or no, we can do the test. But I did want to show some data that we published that actually resulted in the changing of the IAS and DHHS guidelines about resistance testing at low levels of viral load. And that's data we presented that showed that really if you get a resistance test with the low level viral load and patients have stayed on the same therapy, we followed up what happened to them and asked the question, was this low-level resistance test actually predictive of virological outcome? And the short answer is yes. We looked in this slide in people who were on NNRTI-based regimens, and this is the time that it took for patients to go from whatever their viral load was to above 1,000 copies per mil. And the blue line is if you don't have resistance to anything, and the red line is if you have resistance to something. And you see a clear distinction between the two. If you're resistant, you do worse than if you're not resistant, which makes a lot of sense. But what was important was it didn't matter how we cut the data, whether that was overall, whether it was you were on an NNRTI-based regimen or an unboosted PI, boosted PI on another regimen, whether we restricted our analyses to only the very lowest level of viral load or the moderate level. Didn't matter whether there were sequence mixtures in there. In other words, whether we were just amplifying one molecule to start with, such that it was essentially a clone or an absolutely constant sequence throughout the whole thing. No matter how we slice it, resistance by our test predicts bad outcome. So again, that makes me quite reassured that we can actually do this, and especially since we have been doing this for the longest time. The other thing is there's a dose dependence. The more drugs you're resistant to in your regimen, the worse it gets. So everything does work and sort of make sense from that perspective. So we can be reassured that the low-level viral load testing works. But what's I thought was interesting was that actually even failing to get a test result was informative. If you compare a test result that says that you're completely wild type, you do okay, but you do even better in those patients where you ask for a test and we say we can't do the test fails. And I think the rationale for that is that I think a lot of the time that we can't do a test, it's because that viral load test is actually a false positive. The reason we can't get you a result is because there's no virus in there. And I think that's probably more common at the lower end. I don't think, I think some of the results, even in the 250 range, are false positives. It's not an assay, it's not a blip at adherence or anything like that. It's just the viral load says there's 250 copies, but there's a large margin of error in there, and maybe the answer is 0. So I think at least some, not all, some of the failures can be explained by there just being no virus in there for us to do the test on. But obviously I think adherence is an issue as well. The other thing you can do is ask us to see if there's any drugs in that sample. So it's not like a TDM. One of the things we're investigating is whether giving physicians information about whether there's any drugs or drugs roughly in the right level would be useful information. And this started from our analysis of that same data where we looked at patients, looked at the interrelationship between adherence and drug resistance. So in this case, adherence was measured by follow-up prescription refills, whether folks took them, refilled their prescriptions on time. And perhaps not surprisingly, if you're completely non-adherent, it doesn't matter whether you're resistant to the medications you're not taking or not, because you tend to fail pretty quickly. And as you become more and more adherent, you get a clear distinction between resistance or not. So, you need to take your drugs and you need to be not resistant to them for them to work ideally. But we thought to ourselves that we could actually give physicians insight as to whether patients are adherent to their medication or at least getting the right drug levels or not by using that same sample that we use for viral load testing, that we use for resistance testing, still a little bit left over that we can use and measure drug levels in. There is another thing that we're doing in British Columbia with the data, because we're allowed to do research studies on the BC proportion of the data that we collect. And this is what we're calling advanced phylogenetic analysis. And what this means is we're drawing family trees of relationships of the viruses. And we can identify groups in which there's very closely related sequences. And this tells us that when there's closely related sequences, that there's sort of a historical link between those patients. So, for example, if you've got a group of injection drug users and they transmit virus from one to another very quickly, the virus doesn't have time to evolve in one person before it's passed on to the next person. Now, we're not doing this, we can't do this to tell who infected who. We don't even want to know who infected whom. So what we're doing is all of this type of analysis is done anonymously and at the group level. So we're looking for clusters of viruses that are closely related and what the characteristics of that group of people are. And we're staying desperately away from any consideration of the who infected whom question. And we can do this because we've got this huge database from British Columbia with 27,000 sequences of viruses. And we realized that this is actually the most intensively characterized infectious disease on the planet ever. It's from 7,000 people, and we can look and identify closely related clusters, almost about 750 closely related clusters from about half of our population, where we can say, your virus is very similar to your virus and your virus and your virus. And we got this pretty picture. This is just, you're not really intended to get anything other than a general feeling from this. This is about a quarter of the map of BC's transmitted virus. And you see these little clusters. You see groups of 1 or 2 or 4 or 5 people, but also some huge groups that have, in this case, 300 people in them. And another group over here has 50 people in them. And we've taken these clusters and we've looked at the characteristics of what the groups are in the clusters and found that our largest clusters of very closely related virus sequences come from the IDU population. We've got groups with 300 or 350 sort of people in groups of 300 or 350 people with closely related viruses. And what's also interesting is that when you look across all the other clusters, the much smaller clusters, some of them are IDUs, some of them tend to have lots of MSMs. We've color-coded the IDU clusters in blue and the MSM clusters in red. And really, you don't see many purple or black ones, which would be consisting of clusters of groups of infections with, lots of mixtures of both IDU patients and MSM patients. These are separate epidemics. They're not talking to each other. And in fact, when you think about it, really, we're not dealing with an HIV epidemic in British Columbia. We're dealing with about 700 tiny, completely independent epidemics. And it probably gives you an idea, this data, analysis of the data this way, gives you an idea of where we'd get the most bang for our buck in terms of coming up with interventions. So, for example, we've been looking at the growth of each of these individual clusters over time, and our largest clusters have pretty much stopped growing. We've done this treatment as prevention, expansion of HIV therapy in BC, and it's really led to the leveling off of the growth of these largest clusters. So there's not much more we can do. These things aren't growing anymore. We're going to get the most bang for our buck by intervening on the clusters that are growing the most quickly. And in BC, that happens to be these little red ones that turn out to be mostly young MSM populations that are, we do the modeling and we can show that, we're on the exponential phase of expansion in these guys. And the best bang for our buck would come from interventions targeted at our young MSM population. this is all analyses that probably make sense and are consistent with what the public health guys might think anyway, but it's all based strictly on DNA sequence analysis, sitting in your office without having to leave. I'll change topics entirely for a bit and talk about the integrase inhibitors. So we found integrase inhibitor use is probably, well, I'm thinking likely the same as in Ontario, not sure. We still have we've still had a steady number of folks that are on raltegravir, but as the drugs become available, an expansion of the number of people on elvitegravir and more recently on dolutegravir. And the update in terms of resistance to the integrase inhibitors is it's still pretty darn rare. In fact, only 4% of our tests done to date, have had any inferred raltegravir resistance, even though it's been around for a while. And so things are still looking pretty good in that sense. But a limitation is we don't really know, because there's been so few failures for dolutegravir, one of the questions is what actually are the genetic determinants of resistance to it? We're not really sure completely. So one of the things we're doing is culturing the virus in people to get enough data from dolutegravir, elvitegravir, and even raltegravir failures so that we can say that this mutation does that. One thing that has come up is the impression that there's something particularly special about dolutegravir resistance that might completely prevent resistance selection in vivo. Personally, I think that's about as likely as our skater doing that sort of thing. It's probably not likely to happen. I think that we will see dolutegravir resistance in vivo selected from naives. The reason that I'm saying that is that we've been doing some phenotyping where we grow the virus up and say, well, do you have dolutegravir resistance or not, or other drugs? This is the second patient we looked at. This is the line for how much drug it takes to inhibit the wild type virus, is shown in the red. There's a little dotted line there that says how much drug, did it take to inhibit the virus before therapy. So before therapy, this guy was entirely wild type. After therapy, his virus has changed. It's now had a shift in IC50 to raltegravir, elvitegravir, and dolutegravir, but not a subtle shift. This guy's got 100-fold shift in IC50, and this virus is perfectly happy. So there's no question in my mind that there's nothing special about dolutegravir other than it probably takes a couple of mutations to pick up resistance to it. And what's happening is, like all the other drugs, we're not leaving people on failing regimens for years and years and years that it takes to pick up 2 or 3 or 4 mutations. There is data that suggests that having a couple of 2 mutations, say in particular, don't worry about what they are, 2 of the common mutations that you can pick up, 148 and 140 mutations, you get 3 or 4 or 5-fold shifts in IC50. So that's the drug beginning to lose its activity. But as you pick up 3 or 4 or 5 mutations, you're just going to get more and more resistance. And this is exactly the same picture we see with the boosted PIs. It doesn't take 1 mutation to blow up the drugs, but it takes the accumulation of 3 or 4 or 5 mutations, and that's it. The drug is done. What we don't have is sufficient data from patients who have been failing dolutegravir or elvitegravir regimens to be as confident as we should. So if you do have them, let us know, and you can ask us to grow up the virus in culture, and we'll phenotype it and add to our knowledge of what causes resistance to these, what's the explanation for resistance to these, to the newer drugs. And the same thing's true for HCV as well. We don't really know all the ways that you can fail and pick up resistance to the HCV drugs for the most part. So I do have a quick summary of the integrase inhibitor resistance data that we've collected in 2014, at least until Friday. There probably weren't any major changes on Monday, so pretty fresh data. We've done roughly 1,500 tests. About 3% of those tests have any Dolutegravir resistance, according to our algorithm, which says, which identifies the mutations. About 57 out of these 1,500 had Dolutegravir resistance. So I think, surprisingly, it looks like it's even easier to pick up Dolutegravir resistance than Raltegravir resistance, and a lower level, but still actually a not insignificant number of folks that we believe have Dolutegravir resistance. So clearly is happening. We don't know much about the treatment history of these patients outside the ones from BC, though. We are trying to come up with new lab testing methods that are based on next generation sequencing methods that will essentially look no different to you from the outside. The viral load cutoffs will be exactly the same. The processing will be exactly the same. It'll all be exactly the same. From your end, you'll just get a result that really will look quite similar, but our the new technologies called next-gen sequencing will have a higher, better sensitivity for picking up drug resistance within a patient. So right now, if you've got about 20% 20% of the virus's population within an individual has drug resistance, we may or may not be able to detect that. That's about the cutoff for our current assays. The next generation methods that we're moving to will be able to detect down to about 2% of a virus variant within a patient if you've got a high enough viral load. Down around the very, very low levels, it won't make any difference because there's no molecules to find 2% in. You've only got one molecule. It either will be or won't be drug resistant. But we're moving towards these new technologies. It has been a bit of a challenge. The technologies are changing all the time, so it's hard to know exactly what to do. We've had some technical difficulties in actually implementing the technology. So we've been thinking it's been coming along in the next 6 months for about 6 months. For a couple, every 6 months has been moving 6 months further down the line. But I think within the next little while it will come. The data is amazing. There's a lot of data. We get coming off of this thing is 1 million pages a day off of these sequencers that we have to deal with. So we have to regenerate all of our stuff. But what it'll all come down to, that whole 1 million pages a day, is going to be a 1-page report for you that pretty much looks like the current one, except it's going to have all the drugs except for T20, because nobody's on T20. And if you're asking for T20 tests all the time, we're trying to figure out why, because we keep getting all these test requests for T20 resistance and nobody's on the drug. So all of the drugs will appear on one form, and it'll 1 page, and it'll look sort of more easy to interpret, I think. So that's the future, probably within a year, I think. So you'll know for sure that your patients won't have any integrase inhibitor resistance. We are also moving into the HCV world because the drugs are a little expensive from what we've seen. And kind of like everyone else, we're not sure what we're doing, but we've decided to go with the herd and move some of our research towards the HCV world. With the summary that so far everything works, and everything works, seems like it's going to work well. But, we've been treating infectious diseases for a while, and there's always some people that things don't work in. And so we're developing methods to look at, right now, initially the Q80K one, which is a good one for saying, are you a good candidate for taking Cimeprevir or not? Turns out that about 50% of the genotype 1A population in North America end up having this mutation, which decreases response to Cimeprevir in combination with interferon ribavirin. Probably in different virus backbones, it doesn't make any difference because it doesn't wipe out the drug. It just takes a little bite out of the drug's activity. But nonetheless, we offer this as a screening test for patients considering going on to Cimeprevir, but it also gives us insight into boceprevir and telaprevir resistance, and in fact, already all of the next upcoming NS3 protease inhibitors, which are part of the regimens. And as a quick update as to where we are from the tests done in 2014 up until Friday, we've done about 1,100 tests so far, and indeed in Canada as well as in the United States, the Q80K is prevalent at about 50% of the population. But we have also detected really a startling amount of other mutations that would confer telaprevir, boceprevir, and resistance to some of the other drugs. We don't know, this is what drives me crazy, we don't know what therapies these guys were on, so it would be wise to put this sort of data all together so that we can know what patients are taking and what their mutations look like. But I think a lot from talking to people, these mutations were in people who were on the drug, who came off the drug, and the dogma is these mutations disappear very quickly. At least in some patients, they weren't disappearing very quickly at all. So it may have considerable relevance in the future as to the accumulation of mutations in HCV in the same way that it did for HIV. But again, because there's so few failures, particularly on things like sofosbuvir, where we have the data, we really have to make sure that we systematically collect all of the data and all of the samples from folks who are failing on their HCV regimens so that we can actually make sense of the data that we're collecting. So I'm going to finish up there, ask for a couple of things actually from you guys. Maybe one would be change the minimum. I don't know what the minimum in Ontario is. For some reason, the provincial health labs have put on different minima that they'll actually mail samples to us. I think this might have already happened, that they'll send samples to us for doing testing in the range of 250 copies or above, or anytime you really need to know an answer. One is to stop ordering T20 resistance testing unless there's some reason for T20 resistance testing to go on, because we still get hundreds of these a year, thousands of these a year, and we're trying to figure out why. One is to consider using the sequence data that we collect more systematically so that we can really map out across the country how transmission is going on and do something about it. Let's try and avoid blowing up the NNRTIs. And we can, I think, add the clinical and the laboratory data together to work out what the effects of drug resistance phenotype are in particular samples where we have small numbers of failures, and or look at the drug levels in all failures and see if all of this data together leads to better patient management, which is what we're after. So the summary is, although I'd like to retire, not quite yet. We can't say that drug resistance is disappearing. We'll cheerfully test any samples anyone asks us to do. We've expanded to HCV. We actually now have a next generation method that can do the whole HCV genome in one go. So we're ready to go there. And I think we can improve our collaborations between the research testing and the clinical care to optimize therapy. And that's all from me. I'll take any input. Anyone? And Peter, out there.